I should start by mentioning that none of this work would be possible without an extensive list of collaborators and graduate students and postdocs. My group is sitting here, so many minutiae about the talk today will probably be difficult for me to pull up. So I will point you to them for details. In particular, I like to highlight some names in red. These are graduate students who are in some sense the engine behind this work. So Hyman is here. He's a PhD student working with me, DJ as well. Matt is not here. I co-advise him with Professor Sharon Huang. The names in blue over there. Oh, this slide is a little outdated. Troy is no longer at Argonne. He's at AI too. But I give them special mention because they were very instrumental in the high performance computing side of these studies. So they were able to do the software engineering to allow us to train models, machine learning models on upwards of 100 GPUs. So it's not an easy task at all. So, okay. So with that, let's continue. We all interact with the weather, right? And with ongoing climate change, the weather is getting more and more important in various facets of daily life. This is a slide from 2023. I should probably update this to 2024, but the chart on the left actually shows, let me use a laser pointer. The chart on the left actually shows events, 28 separate events that individually led to billion-dollar plus economic damages across the US, both continental and otherwise. You can see the whole gamut of things from flooding to tornadoes to heat waves, hurricanes. Just 28 of them are enough to cause, $1 billion of damage each, right? Overall, the economic losses for annual economic losses related to extreme weather are estimated to be around 100 billion, 10 to 100 billion. So it is vitally important to predict the weather accurately, especially in cases of extreme weather. If you look at the fatalities associated with weather, directly with weather, of course, not related to the economic damage, then you're looking at around 100 fatalities annually, and this number is growing again with climate change. So again, this slide is from 2023. Every year, it's getting more and more extreme. Okay. So the reason why I'm giving this talk here today, and probably many people like me are giving this talk at other institutes around the world, the concept of machine learning for weather prediction is because in recent times, there have been some remarkable advancements in data-driven modeling for the weather. So if you're not aware, the weather you get on your phone comes from extremely costly physics-based computations. So there's a physical laws that you can use to define the evolution of the weather. But recently, purely data-driven methods. So if you just have data and you use machine learning models to predict the weather by ignoring physics for the most part, you're starting to get remarkable improvements in accuracy as well as computational speeds compared to what you get on your phone at the moment. Right? These are still not operational, but they're getting very close. In particular, I have some references over here which really captured the imagination, both of the computer science community as well as the earth science community, and popular science as well. So there's one, and these are very readable. This one reference is from NVIDIA. This is ForecastNet. They essentially, folks at Caltech developed a new machine learning architecture for dynamical systems. They collaborated with NVIDIA and then deployed this on 1,000 GPUs in collaboration with Lawrence Berkeley, and built the first high-resolution weather model that was competitive with something that comes out from the National Weather Service, right? This is a paper that was it was on the archive about a year before it was published in Nature, but this was a small team in Huawei in China who put out a paper. They call it Pangu Weather, and this was the first reference that actually outperformed a deterministic forecast from the European Center for Medium Range Weather Forecasting, which is the premier weather forecasting agency in the world, right? And then basically what has happened since then is the so-called arms race of weather. We've had all the major companies based around the Bay Area, Google, Microsoft, so on and so forth, have thrown their hat into the ring and used their and set up teams hired extensively to try to beat each other in getting more and more accurate weather forecasting. So there's a website you can go to. This is updated frighteningly quickly, unfortunately, where you have various weather models that are pitted against each other with respect to ground truth, which is, we'll get to what the ground truth is in a bit, right? And so, so it's exciting times, right? So you're able to basically see in real time how advances in accuracy, which took several decades in the classical weather forecasting paradigm, now take months, if not less, right? What was the Hyman? What was the number? If to get 1% improvement in skill, you need so many years in classical. Do you know? You don't remember. There is a number. It's a year. It's around a year. It's in the order of years, but the same thing is now order of months instead, right? So that's why people are very excited, right? And I can give you an example of this through, again, a slide that is slightly outdated, but it gets the message across, right? So I have 4 panels over here on the left for moving pressure contours over continental United States. You know, if you've ever watched the Weather Channel, this is what the people are standing in front of. If you think about the top left as ground truth, I will explain what ground truth is in a bit, and you compare it to predictions from numerical solvers, so physics-based solvers that have been used for the last 50 or 60 years, then you will see that, at least to the naked eye, these machine learning models are doing as well, right? And if you are to then look at more quantitative analyses, for example, skill is something like accuracy, then you start to get some pretty remarkable trends. For example, machine learning models are actually starting to outperform physics-based models in weather forecasting, right? One thing I want you to take away from this is, yes, they're starting to outperform things that have traditionally been used, but they're also way, way, way cheaper to get. These machine learning models can do very rapid inference on much smaller computational hardware. So there's a double benefit. A nice example of this is a hindcast. So hindcast is basically you do a weather forecast for a condition in the past, and you see how the forecast may have been, and because you have the ground truth, you can actually compare against it. This is a typhoon in 2018, Typhoon Kongre. The European Center for Medium Range Weather Forecasting predicted that it would hit China, right? That was the blue line over here. And in reality, it did not. It went ahead and hit South Korea. The forecast was wrong at a certain lead time. Of course, these forecasts are dynamically updated all the time, so it's not like people just gave up after the initial forecast. So the forecasts were updated, but at a certain lead time, there's only so much predictability you can get with the classical forecast model. But the machine learning model, in this case, Pangu Weather, was able to actually forecast accurately the track of the hurricane at a much cheaper cost, right? So this is why people are so excited about these things, right? Okay. But really, if you go down into the guts of how these models work, they're not much different from how a classical weather-based model works, like a physics-based model. The idea is that you solve a time series learning problem, right? Except that it's defined in a spatiotemporal sense. Instead of predicting literally a time series of a vector valued feature, you predict a time series of images, kind of like video generation, for computer scientists, right? And if you think about classical numerical methods for solving differential equations, if you're not familiar, you set up a differential equation like this, and the way to solve this is typically the easiest way to solve this is to so-called discretize this in time and then use like a time stepping scheme. So a discrete autoregressive prediction where the input gives you the output goes back into your model, gives you the prediction. So it's very similar to a time series forecasting scheme as well, except that the G over here on the right-hand side in your differential equation comes from the laws of, well, the best known laws of the atmosphere, right? That is what is now bypassed in these machine learning models. You learn what the G is, right? And as usual, once you decide to abstract away the G with a function approximator like a neural network, then then that's the start of the engineering part of your project. What sort of neural network do you have to use? What architecture is good? What resolution is good? How do you regularize it? How do you train it? All those things are where a lot of these models start diverging, right? But at its heart, all of them are very similar in the general sense. Okay, so in our group, we have a project underway that looks at the weather. It's called the Stormer project, and it's actually it builds off of a defunct short-term project that was set up at Microsoft. That project was itself called the Climax project, where the idea was to build a transformer-based machine learning model for predicting the weather. Microsoft shuttered its team looking at the atmosphere, but we were able to pick it up because they open sourced their codes and fine-tuned their model to actually build our own weather model. Some details over here of what we actually used as the training data. So the variables, etc., are not important, but what is important is that there is a benchmark data set out there, which has also been, in some sense, the spur for all this, enhanced activity in machine learning for the atmosphere. It's called the Weather Bench data set. It was released in 2020, and that kind of marked an inflection point for how many models have been generated. You can find details of our data set over there. What it uses is a data set that was released by the European Center for Medium Range Weather Forecasting. It's called the ERA5 dataset, and this has kind of been, in some sense, the go-to for anybody who's trying to learn something for the atmosphere. Now, atmospheric scientists in the room may say ERA5 is not ground truth. I fully agree with them, but computer scientists will say we need to start somewhere, right? And there are things we can do after this, but that's probably a matter of research, right? So ERA5 is something called reanalysis data, which means it actually used numerical simulations to generate the ground truth, but the numerical simulations were corrected using observations from satellites, from radio sondes, from ship buoys, and so on and so forth. So it's a more enhanced numerical solution. So I want you to look at the reason why many of these machine learning models are outperforming numerical simulations is because the ground truth that they are trained on has been painstakingly constructed to be better than numerical simulations, right? So that's why it works. Okay, but just to give you a sense as to how costly these trainings are, right? Deploying these things is pretty cheap once you've trained them. Training these machine learning models is quite costly, but it's a one-time cost. So for example, this particular project that we are developing, that we did develop, we just did fine-tuning, but just to do fine-tuning for this with 100 million unfixed parameters required 40A100 GPUs, 8 hours of training on 40A100 GPUs, right? And this is not a very fine resolution. This is not a very useful weather model yet, right? So if you discretize the Earth on a very fine grid, then your weather models need much more time to train. All right, so you can see this is a prediction from, well, that's a very quick one. Sorry, let me run it again. This is a prediction from our machine learning model, which you can see it captures the dynamics of in this particular case, atmospheric rivers quite nicely. So it's able to learn some of the underlying physics without us explicitly specifying them, right? All right, so how do we construct our weather model? Well, again, we can choose to have a resolution both spatially and temporally that is, of course, use-driven, but also in this particular case, since this was a starting point, we used a coarser resolution both spatially and temporally. So our weather model gave us one-step prediction 6 hours into the future. So it was not a prediction 15 minutes into the future, which could be, of course, very valuable as well. But this is a prediction 6 hours into the future. But like I said in the general slide, you can roll out these predictions like and get predictions up to multiple days into the future. That's how this works, right? Okay. So just an example of how this model was actually used. Late during COVID, there was this large extratropical cyclone in the northern Pacific, which broke the North Pacific pressure record. Your classical numerical-based models actually failed to track the trajectory of this cyclone effectively, but Stormer was able to pick this up quite nicely 5 days in advance, right? So that was quite nice. Okay, you can find details about this work. This was published in Europe's. Okay, so what was the sort of the the specific detail about this neural network architecture that made this kind of useful for predicting the weather? The important thing to note is that we're not very far removed from computer vision, right? So we're still using things that are very natural to computer vision, such as vision transformers, or in some case, convolutional neural networks. We're just throwing in these sprinkles of things that make it more suitable to the underlying physics of our problem, right? So for example, in this particular case, we used vision transformer-based layers or modules, which well, not modules, blocks, which we sort of patched together. But an interesting thing that we incorporated in our model that actually gave us a significant benefit was this concept of adaptive layer normalization. So if you're familiar with regular layer normalization, the idea is that the output of every single layer in your neural network is centered, right? So it's zero mean unit variance again, and this is something that is guaranteed during the training as well as the deployment. Here, this centering is adaptive, right? So to center data, you need to calculate its mean, it calculates variance, and then subtract the mean, divide by the variance, and you get a zero mean unit standard deviation data set. Over here, we did not calculate the mean and the standard deviation of the data as it exits the layer. We predicted what the mean and standard deviation is conditioned on the input. So it was adaptive centering, and this led to a pretty impressive increase in performance. But aside from that, the only interpretation of the data that we had to map to how computer vision works is simply recognizing that the different variables of the atmosphere are like images, right? So if you think about an image, a photograph, a color photograph, you'll have red, green, blue as channels. In this particular case, you will have multiple channels. Individual channels could be temperature, relative humidity, wind speeds at different heights, pressure levels above the surface of the Earth. And so you will concatenate them in the third dimension, right? The two dimensions are latitude and longitude. The third dimension is all these variables. And then you'll pass this in as an input to your vision transformer, right? And so actually yesterday, right? Oh no, it was day before, we actually had someone from the Aurora project from Microsoft. So Microsoft shuttered the Climax project, but started another one in Europe called the Aurora Foundation model, which one of my colleagues from the University of Pennsylvania was leading. So he was here visiting and gave us a talk on that. Very interesting stuff. I don't know if you guys were there. But they are also using a similar idea. They're also using a vision transformer to predict the future, right? Another thing that we built into our model to get an improved performance was this concept of randomized predictions, right? So if you think about, let's say someone comes to you and says that I want a prediction 1 day from now, right, for the weather. And our model can give you 6-hour predictions. So how do you go out to 1 day? Well, the first answer is, well, you can make 4 predictions in a row, right? 6, 6, 6, 6, and you get to 1 day. But you could also, for example, have another model that gives you 12-hour predictions. So you can go 6, 12, 6, right? So there are many combinations that you can use to go out to 1 day. And so the one thing that we baked into our model to give you combinations of forecast was this time delay, well, this ability to be conditioned on the time step as well, right? So instead of going directly to 24 hours with one model, we don't want to do that, or having a continuous input for time, so giving a certain hour and having a particular prediction, or using the general concept of one-step prediction, 6666. We had something called a randomized iterative forecasting, in which case your adaptive normalization layer, which I introduced, where was it? Here, right? This adaptive normalization layer in my transformer architecture is now conditioned on the time step, right? So I will first give my model a particular time step. Give me something at 6 hours or 12 or 18 or 24. That goes in and changes in real time, in deployment, goes in and changes how the data is going to be centered. And you can think of a structure being moved, right? That's how it works. And that will give me a forecast. Now, instead of 6 hours later, it'll give me something 12 hours later, right? So now, if I go back to the schematic over here on the extreme right, if I have to go up to 24 hours into the future, I end up with lots of combinations, right? There's a fixed finite set of combinations. I can collect all these combinations, right? I can have one combination 6666, one combination 1212, one combination just 24. I can collect all of these, and I will get a different prediction from each of these, yes, right? I can then find the expectation of all these predictions and get you ensembles of weather forecasts for effectively free, right? So that is one thing that we added over here, and the ensemble mean. So the expectation of our prediction actually brought us a significant improvement in accuracy over just using the direct forecasting technique, which at that point, when this paper was published, was quite novel, right? Now other models have started using this as well. All right. So when we compared our performance, again, this was published in 24, so things are moving so fast in this space, it's probably outdated. So I'm not dealing in absolutes. I'm not saying ours is the best one, right? But when we compared it to, for example, the published work of Huawei, Google back then, which I think that improved the results quite a bit, and also compared it against IFS. IFS is operational models, which are used, for example, for weather forecasting now. We saw a pretty significant improvement. So the green line is ours, the root mean squared error is a metric, lower is better. The dashed line over here is climatology. Climatology is essentially it means that you basically take if you have data for 40 years for what is tomorrow, the 10th of April. If you have data for 40 years for the 10th of April, you just average all the 10th of April, and that's your prediction. It's a free prediction, right? Not free, you just look up from memory. But you should be able to beat that, right, at least. So, and you see that we are generally able to beat that when we make predictions for the first 14 days, 2 weeks. After that, no point anymore. You can just use the average prediction, right? So our goal is to stay as below that as possible, right? And again, in comparison to these other models, you can see that we were better, but like it's an active area of research. All of them are, and especially it's very difficult from academia to compete against software engineers who are paid, I don't know, $300,000, unfortunately. So yeah. Okay, so but we were very happy when there was someone from, like, do you guys know who made this plot? Was it Mike Pritchard? This from NVIDIA? Okay, someone from NVIDIA, one of those companies, basically took the time to actually do a literature survey of all the weather models out there and actually evaluated them, you know, kind of, and compared all of them together. And what came out of this is something really remarkable. So you have the x-axis as time, which starts in Jan 2019. The y-axis is percentage skill with respect to an operational forecasting model. And you see the first few deployments of machine learning for weather forecasting were by Peter Durbin in late 2018, and you can see you're getting around 20% skill. So basically, you are your skill is kind of, you can think of this as a metric of accuracy. You're getting really poor accuracy compared to operational weather forecasting models. But you see over time how this plot goes up to the right? So the models keep getting better. People have more access to compute. The architectures get more and more customized. What really caused a big sort of outpouring of excitement was this model by NVIDIA. I had the citation up in my second slide or my third slide, ForecastNet, which still didn't beat any of the physics-based models, but this is one physics-based model, very close to 100, but it was getting there. So it was able to get 7 days of accuracy below climatology rather than 14. And Ryan Kiesler in 2022, I don't know how, used how many GPUs, like one or maybe less than 10 GPUs to train a graph neural network module and beat an entire company that I don't know, has a probably $1 trillion market cap at the moment, right? So that caused a huge furore as well. But you see now these mods are all starting to cluster over here, but they're starting to cluster over 100, right? So they're getting better than these physics-based models. And you can see Stormer it should be somewhere here. Yeah, there it is. Yes, that's our model as well. So we are also quite competitive at the top. Okay, so I will stop there and see if there are any questions before I go into the next part of my talk. Yes. Yes. So the question is, why is the adaptive layer norm better than the standard layer norm? In these particular applications, you have features that move. They advect, but they advect in a coherent manner. You can think of a shock wave, right? It's moving in. And so the idea of centering data, but having it conditioned on the time kind of feeds into that. If you have a larger time step, then the structure moves longer or further, right? So, and for that reason, you can condition movement of structures based on the time step. That's kind of the idea of the adaptive layer normalization, right? Yes.
So you did talk about when you do the forecast, the 6, 12, 24, and so on, you get the random component.
Yes, yes.
But errors are additives. So you find your forecast for 6 and then for 12 and so on.
Yes.
Yes,
Absolutely.
So when you do your ensemble, you're actually doing your ensembles that comes with different level of uncertainties.
Different
So
amounts
it's
of
a very different ensemble from what is generally talking methodology.
Yes, absolutely. Okay. I did not say it's related to sampling from a distribution. This is just an expected value from some distribution. I don't know what it is, but it's you're absolutely right. That there are growing errors.
I mean, basically, this ensemble means that you're computing.
Yes.
Very different than
Yes.
Smoothing.
Yes. And another thing I didn't mention, but since the question came up, let's say we go up to 14 days, right? I mean, there are so many combinations to go up to 14 days, right? I mean, one day, yes, a few, 14 days, several. We actually have a meta model that selects the best combination. So from our training data, we actually find what are the good combinations. And let's say we find that 6, 12, 12, 6 is the best combination for a 1.5 day prediction. And and since there are many possible combinations, we'll select the top K combinations and we'll just keep them and then use that as our ensemble, right? Because the growth is too large for the size of the ensemble in that sense. But for a small forecast, you can use every number if you want. Okay, good question. Question? Okay. All right. So that was weather. Okay. So one of the realities of doing research in machine learning for weather is that competing as an academic group is virtually impossible, right? The amount of computation resources that you have access to as a scientist at NVIDIA or Microsoft or Google, it just blows your mind. You cannot, or Meta, you cannot on demand get access to 500 GPUs, unfortunately. Right? I mean, I'm looking at the ICDS director over here, very pointedly. But So in some sense, a lot of the work that is happening in machine learning for weather forecasting now is starting to verge on the very compute intensive side. So algorithmic developments require, or improvements in accuracy either require you to train on much larger data sets or require much larger amounts of compute. And so it's kind of it's not a good idea if you're an academic, because you probably expose your group to a lot of risk in the sense of trying to solve a problem that might be solved overnight by someone in industry, right? So, but fortunately, there are still some very important problems in forecasting for the earth sciences that these large software, well, not really, they don't sell software, but large tech companies are not that invested in, right? And the problem that we are interested in is longer term prediction. So if you think about weather is something that is directly connected to a notion of profit, right? We talked about the $100 billion of economic losses annually. Longer predictions, which fall into the range of medium range predictions or season to season predictions, or even longer climate timescales, right? Centuries. These are things that are also, of course, very important for economic activity, but not perhaps to the Bay Area companies quite yet, right? So that's one space where there is a slightly reduced amount of research activity, but it's still equally important, right? If you think about the questions of how there may be trends in extreme events happening at a particular geographical location because of carbon dioxide emissions 100 years into the future, that is an important problem, because our grandchildren will be facing those events, right? So this next part of my talk is going to talk about long-term predictions, right? How do we modify the thought process about solving these problems when we say we still care about short-term, but maybe we care more about long-term statistics rather than point-wise accuracy of our predictions, right? And typically, the concept of long-term prediction is one that relies not so much on the question of 100 years from now, what is the weather going to be like at State College? It's not important. In fact, it's impossible to predict. It's a chaotic system. But what is important is an analysis of PDS, of statistics, right? Statistically speaking, can you tell me something about the weather in North America, right, 100 years from now? That is a more realistic question to ask when you're looking at centuries of forecasts. All right. And here's the funny thing. So one of my colleagues, actually, Ashish from UC Santa Cruz, he's a faculty over there. He's collaborating with us quite extensively. While he was wrapping up his PhD, he decided on a whim to actually download all these AI for weather models, right? And basically let them run for centuries, right? Which, of course, they're not trained for that. They're only trained for 14 odd days. And as expected, most of these models within either weeks to months, cause the oceans to boil, or the atmosphere to burn, I don't know, something like that, right? Completely unphysical, right? And this makes sense because the climate of the planet is something of an invariant property, right? So if how many people have simulated the Lorentz 63 dynamical system? I'm talking to a crowd of computer scientists. The Lorentz 63, you should do it. It's the butterfly effect. How many people know about the butterfly effect, right, in chaos, right? So it's a three-dimensional dynamical system, which no matter what you start the initial condition as, it falls onto the wings of the butterfly, right? That is an inherent physical property of that system, that you will end up on the wings of the butterfly, right? And so there is such a property of the Earth's planet, of the Earth as well, which is that no matter what the initial condition is today, which is the weather, you will end up on the Earth's climate, right? Now the climate may change, so it is a measure, or is it an invariant statistic that is changing, but it's changing at a climatic time scale. It's not changing at a weekly or monthly time scale, right? So, and this is the big problem with Many people who don't understand climate modeling, right? They say, oh, you can't predict the weather 2 weeks from now. How can I trust you when you say that it's going to be 5 Celsius more warmer 100 years from now, and the oceans will be several feet above? It's because it's a different problem. That is a statistical problem, and this is a point-wise problem, right? Of course, we cannot communicate to that the other side, and then yeah, you get what we have today. So so this part of the talk is now going to talk about the climate problem, not the weather problem. Okay. So if you so what Ashish did in that paper, which again is a very nice read, is for the models that did end up being stable. That some of these models they blew up, like I said, completely, and completely garbage results. But for some of them still gave you something that looked like weather. He plotted some statistics. So these statistics, if you look at them, are over latitudes. So over latitudes averaged along the longitudes. And they are, for example, pressure on the left, wind speeds on the right. And if you look at the black line over here, the black line is coming from 40 years of observations that the European Center for Medium Range Weather Forecasting, ECMWF, has given us. And there are some properties over here that are inviolable. These, for example, this on the right-hand side, these wind speeds that you see, the U250, this is wind speed at a particular height above the surface of the Earth. They should show this dipole. In fact, that dipole has driven a lot of human civilization, things like the trade winds, right? So your atmospheric model for the climate better captured that dipole, right? Because that is a property of the Earth's climate. These other weather models, some of them did not capture it, others got the location of the dipole wrong in the latitudes. So this is a diagnosis of the fact that, or evidence of the fact that these models are trained for short-term prediction, but they cannot get the climate right? So we need to do something special to get the climate instead of just the weather. Okay, so that brings me to the project, another project that we're running in our group. It's called the Lucy project, right? We have to have a trendy name for everything, right? So the Lucy project is called the Lightweight Uncoupled Climate Emulator. And the idea over here is to really think about our forecast problem from the climate perspective, right? And that affords us quite a few luxuries, right? Firstly, because we care more about statistics and not about point predictions, nobody's going to ask us about the weather at State College or Philadelphia centuries from now, but they may ask us about the general area. You can afford a much lower resolution, so you don't need to have a very fine resolution of your data set, right? What we care about is ensembles. So we need statistics. So we need to have many forecasts or many climate model predictions. So we can afford to have a lightweight architecture. So in this particular case, the architecture that we used is something called a spherical Fourier neural operator. Do you have a schematic of this? I do, yes. So the spherical Fourier neural operator was also developed at Caltech. We added our own sort of fine-tuned features to this, but the basic idea is that if you know what a convolutional neural network is, where you have filters that span your physical domain, instead of doing localized convolutions, if you take a Fourier transform of your flow field, a Fourier transform of your image, and in the Fourier transform, if you do a local operation, it is by definition global, right? So that's elementary spectral analysis. In this particular case, the Earth, unfortunately, is not flat, right? So we are on a sphere, and because of that, we have to not use the Fourier transform, we have to use a spherical harmonic transform. So that's where we call this a spherical Fourier neural operator. We do a spherical harmonic transform, we get representations of our images in the spherical harmonic space. We do local operations in the spherical harmonic space that's similar to convolutions on the physical space on top of the sphere, right? That's the essential idea of one of these blocks in the SFNO. And you can concatenate these blocks just like you concatenate convolutional layers in a neural network, right? Okay. So, and you can use a residual neural network formulation and whatnot. But those are standard neural network details. This is just the specialty of the SFNO, right? Other things that we use to make this a little more accurate for our application, we, instead of penalizing losses of like a mean squared error type metric, which is like just the prediction minus the ground truth, we penalize the loss in the tendency. So think of that as a residual neural network formulation as well. So we want to predict the squared error in the tendency. And another thing that we do is we selectively penalize the predictions in the areas near the latitudes. And there is a reason to do this. It's because, again, the Earth is on it's spherical, but also a lot of the dynamics that happen at in the atmosphere are kind of, especially if you think about things like humidity, they happen very much around the mid-latitudinal band. So there is an emphasis on making that more accurate. But these are, again, design details into how you construct a loss, right? Okay, so let's say we go ahead, we train this. It trains really quickly. It trains on a single A100 GPU in an order of hours. So luckily, we don't have to ask for huge amounts of resources. But the nice thing is we can get indefinite stability out of this model, right? So we can start making predictions for climatic timescales. So what I have on the bottom over here is a prediction for the average temperature. So let's say my model is predicting temperature as a fully resolved flow field. I select the average and then I just plot it, and it tracks at least for 10 years out of era 5. That's the ground truth. Again, it's the best we have. It's able to track that average value very accurately, right? But if you look at the actual dynamics of the flow fields, you're getting quite a lot of rich structure. And this is a pretty coarse grid, but it's still going to give you useful information for the types of questions we ask at a climatic timescale. Just because we care about climate doesn't mean we don't want to, we still analyze how the model performs in the short term. And one nice property we get is that while we're not competitive with those other models that I just talked about, right, because they have very high resolutions, what we do get over here is an ability to beat for persistence. So persistence forecast is, again, a very cheap forecast. It says that the weather tomorrow is the weather today. The weather day after tomorrow is the weather today. So we have, and it's a free forecast, right? And any model that you construct should beat that. It should beat that. It should be climatology, right? So in this case, we are able to beat both. So, okay. Just a visualization here of the other variables that we're predicting. Again, we can see a clear trend that is recreated both in the sense of the seasonal variability as well as the trend. So that is good. When we plot averaged values for the temperature, for humidity, for wind speeds and precipitation, and compare it against era 5, again, our ground truth, we are able to get biases that are comparable and actually lower than many of the benchmark emulator models out there at the same resolution. For example, Speedy is a model out there. I don't have results comparing against Speedy, but we are able to beat Speedy. Right. So what we really care about is the statistics that I mentioned back there, right? For example, the dipole in the UV. This model is very cheap to deploy. You can use one evening and a laptop, even without a GPU, to generate 10,000 years of simulations, right? You can then use that to construct these ensemble statistics. And as you can see, when we now compare these statistics, I'll just refresh your memory with the weather models back here, right? And how they were not collapsing onto the actual ground truth statistics. We're able to now do much better and actually collapse onto those statistics quite nicely. So we're able to recover like the invariant measure of the atmospheric dynamics more accurately with this model. So that's, again, I want you to think about this problem in the sense of how do you learn against a target distribution, but you only have access to mean squared error for individual samples from that distribution, right? So this is the real challenge of a chaotic dynamical system. Short-term forecasts are never enough for a chaotic dynamic. So we have to build some knowledge into your machine learning model to allow you to converge onto the invariant statistics, right? Other things that we get, we don't get everything. This is, of course, inaccessible to someone who is outside the earth sciences domain, but what these plots are showing you are, these are like power density spectra plots, which show structure that correspond to emergent phenomena, right? For example, oscillations in the Earth's atmosphere that show up at certain intervals, such as El Nino, the Mann-Julian oscillation, Kelvin waves, Victor-Rossby. This version of the model that I'm just talking to you right now, for example, captures two major emergent phenomena, equatorial Rossby and Mann-Julian. Doesn't capture the third Kelvin, right? But we have a remedy for that. Again, these are things you can't learn against, right? You can't just put it into a loss function and say, okay, let's try to maximize. And that's how AI for science is different from classical AI, which is if you have a loss function, you try to optimize against it, right? Okay, so if we then go ahead and check, for example, the spectral structure of the fields we are predicting. So remember, we are predicting fields iteratively into the future. We want to make sure that these fields are physically sensible. So there is, in addition to those invariant statistics that I mentioned, there's also this concept of spatial statistics, which is how much energy is distributed at the different wave numbers. You can think of this as taking an image, doing the Fourier transform, and then computing the square value of the Fourier modes and averaging it. We are able to sort of collapse quite nicely onto the ground truth, again, from ERA 5, right? Okay. Another thing that is very, very important for climate, which is this concept of extreme events. So if you think about, so what I have in this plot here, each panel shows something called a return period. So the x-axis of this plot is a number which is in some sense the max value of a prediction. So if you think about, if you look at the top left, that's temperature. A value of 310 over here for Kelvin says that the maximum temperature on the surface of the Earth that day was 310 Kelvin. That's all it means, right? The y-axis says how many years does it take for that to be true? So if the maximum temperature is 310, then in this case, it's a matter of days before it's true again, because it's 310 is not a very high temperature. It'll be coming around soon again, right? But as you keep going right on the x-axis, the temperature rises. You're going closer to 60 Celsius, 70 Celsius. Those don't happen very often, very rare. So you can see that the return period should go up. This makes sense, right? It should be vanishingly rare to have a temperature of 65 as the maximum on the planet. And the ground truth, which in this case is, again, just 40 years of data since we sent up satellites, right? Actually shows that trend of this exponential growth in the return period for extreme events. The very interesting thing is our climate model is able to match that trend. We have improved this, by the way. Climate model is actually able to match that trend as well. So we are also able to generate extremes. So again, something you can't really differentiate and put into a loss function and train it, right? So so this is quite exciting, right? Other things, perhaps in the interest of time, how much time do I have? 10 minutes? Okay. I will go this speedily. So we just computed, for example, the principal components of our return flow fields. And they, again, match the ground truth. Nothing spectacular over there. The other thing that I, again, want to come back to is the fact that our model is exceptionally cheap to train, right? So this is something that, again, going back to the whole discussion of academia versus industry, you can sort of see more possibility for sort of breakthroughs when you have, you know, a 2.4-hour training time for a problem, as against this literature review is probably also not complete. There are many other models out there right now, and I'm pretty sure these numbers are growing a lot as well. So there's other models out there which are training for weeks and weeks and months on huge amounts of compute. So we tried to go the other way to keep it lightweight. The reason I have the blue box over there and on top of our work is there's actually just one more group out there that is doing AI for climate modeling. That is the group that is the company AI2. It is funded by Microsoft. But Microsoft shut down its own climate team and then started another company. I guess that's why. And they poached Troy from us. So Troy Arcomano, who was actually leading this work on our end, is now, he's not a direct competitor, but it's now we can compete with him anyway. So, but their model is a higher resolution model, right? And it was, and they are the only other team out there who's doing climate modeling. I don't know, right? Okay. So some other metrics. A program manager in the Navy said, okay, well, I agree that you've given me a climate model, but does it still behave like the real planet? He said that I want you to take an initial condition and I want you to add some noise to it. And I want you to show that you end up on different trajectories. So this is the concept of deterministic chaos. We proved that we do that, right? So basically, it's not like we are memorizing the climate and just recovering it. We are learning the right dynamics, okay? We are working right now on also assessing whether our model, I mean, we have assessed it, but our model is also able to pick up a warming signal. So when our model is given an exogenous variable of carbon dioxide, so when we add carbon dioxide due to anthropogenic factors as an additional variable that is not forecast, we just assume we have access to it, our model is also able to predict the right rate of heating on a decadal timescale, which is very exciting because then we can solve the inverse problem. What rate of heating will we get if we change the forcing functions, right? So this is something that is, of course, ongoing work, right? And here's the really interesting thing. When we added into this two-dimensional model, when we added carbon dioxide as an extra input, so we got the heating right. Previously, the model was not really giving us the right heating signal. We were getting way more accurate computation of extremes, at least with respect to the 40 years. So what does that tell us? It tells us that, well, don't quote me, I could become a target. But it tells us that by adding that as a forcing, we injected some information into the system that helps us capture the right statistic when it comes to extremes, right? So yeah, so pretty exciting. Again, these are things that it's basically one GPU and one grad student. You know, we were able to do this because of the lightweight nature of this model. Okay, some things that we're working on right now. This is not very interesting, but if you remember the plot about the emergent phenomena, the atmosphere is not running in a vacuum. It's coupled to the ocean. It's coupled to the cryosphere. Excuse me, I'm sorry. It's coupled to the cryosphere. It's coupled to vegetation. So it's a very complex multi-physics system. So the atmosphere by itself is not supposed to be predicted properly. So when we coupled the atmosphere to a model related to the ocean, so we added another variable related to the sea surface temperatures, which the atmosphere interacts with the ocean at the surface, right? But we actually saw that the one emergent phenomena that we were not getting without the ocean then showed up, the Kelvin wave, which is another very nice validation of the fact that adding physics is making our SFNO architecture pick up these emergent phenomena. So, so a very nice playground for seeing how things affect each other. Okay, some bias comparisons against E3SM. E3SM is a model that is the Department of Energy's flagship climate model. It has seen many decades of development. It is a very complicated piece of Fortran code that, hundreds of scientists, many pieces, lots of careers, but we are able to basically match their performance using this model. It goes back to the original discussion of how fast skill is growing in machine learning based predictions for the atmosphere, for the Earth system. Okay, all right. So I have 5 minutes, so I will race through this very quickly. But what we are working on right now, if you remember, our model is extremely coarse. So you can think of our model as predicting something on the left, which is very, very coarse. But many people will say, well, okay, that's good for statistics, but perhaps I want more localized statistics. What do we do then? In that case, we turn to methods related to super resolution. Super resolution, basically, if you're familiar with computer vision, is the idea of reconstructing fine-scale features if you have only coarse-grained information. So this is still work in progress, but we have a couple of architectures that my students are developing that is learning a data-driven map from a low-resolution flow field or low-resolution image to a high-resolution image. Again, given the 40 years of data that we have now, but deploying it on climate projections into the future. This is based on the SFNO that I was talking about. This is a CV, like a vision transformer that is continuous, so it lets you upscale based on a continuous encoding. And if you are to look at some results from this, the top row is the ground truth, again coming from our ERA 5 data. The second row, the input, is something that our model is predicting now at the climatic timescales, which is very coarse. This is North America, by the way, right? Enough for global statistics, but perhaps not for regional statistics. If you are to do a bicubic interpolation, you get something, but it's probably not very satisfactory. For example, you don't pick up features over here in the west, but you see over or the Great Lakes actually also. But if you, how do I play this again? Yeah. But you see with the data-driven super resolution, we're able to recover the fine-scale features of your prediction quite nicely, right? So quite exciting work. And this shows up also in the power density spectra. We're able to, so this is the spectra for bicubic interpolation. We're able to recapture the original spectra quite nicely. Right. Okay, so with that, I have run out of time, but I want to tell you that there's a lot more work that we have to do, right? So there are still some emergent phenomena that we are not picking up in our models. The most important one that several of us interact with on a decadal timescale is ENSO, El Nino Southern Oscillation, right? So it leads to different precipitation, especially in Pennsylvania. We want to add more use cases over here. For example, one use case we want to do is solve the inverse problem, which is if my model is able to predict the heating based on what carbon dioxide was injected into the atmosphere, can we solve the inverse problem, which is if I want to desire cooling or heating, what is the right carbon dioxide removal or injection into the atmosphere that engenders that, right? So that is something that we are looking at going forward. And yeah, with that, I will thank you for your attention and take any questions. So the question is, why was the Fourier transform used? Oh, we use the spherical harmonic transform of the Fourier transform. But the idea is that you want to do convolutions. You want to learn non-local interactions because, again, think of a shock wave. A shock wave is moving in space and time. So the reason it's moving is because it's interacting with its neighbors and information is propagating, right? So we need to find an efficient way for information to globally be exchanged. So when we do the Fourier transform or the spherical harmonic transform, we go to a space which is frequency or wave number where everything is global, right? So anything happening at a particular frequency implies that that information is present everywhere. So you can do a convolution as a local operation in the Fourier space, which makes it immediately global, if that makes sense. Okay, it's more efficient. You could do this using a CNN, but it's just going to cause the number of parameters to blow up. That is our experience, right? And much harder to train. Okay.
Did you say you didn't exactly use convolution? You used something else?
We did not use, well, it is conceptually convolution. So what is convolution? Convolution is filtering, right? So you can do that filtering in a different physical, you can do it in physical space, in which case you actually have to do filtering, look left, look right, average, right? Or you can do it in the Fourier space, which means that in the Fourier space, you do a local operation and immediately you exchange information in the physical space globally. That is basically, so I'm still doing convolution, but locally in the Fourier space is convolution, globally in the physical. Okay. Yeah. Yes.
I remember correctly, in the Fourier, one of the conditions is that the signal is cyclic, basically. So
The signal is what, sorry?
it's cyclic, so that, you know, the beginning of the signal.
Oh, yes, yes, yeah.
Okay. So that means that depending on you break the signal, you might actually get slightly different results because, you know, you're just
Oh, yes.
imposing it. So, yeah, I mean, I think, you know, that if you look at the data for the Earth, if you break it, you know, over the Pacific, for example, the signal versus, you know, over Europe, which is what I think you're getting, should be getting better results because things are more continuous over the Pacific.
I don't know if we looked at that. Did we look at that?
So SFO is using something SFO is using something called spherical conversion. So that's doing this evolution of CNN on the sphere to make sure that the data of the result is rotational invariant. So no matter how you rotate the ball of the Earth.
I understand, but what I'm trying to say is if you think about the signal, right? So any 2 points next to each other, then, you know, they need to be continuous. But that's the only thing you're solving for. You're not solving for the slope. So 2 places where, you know, the gradient is high, they will have. So if you break it there and you do your harmonic, you should get worse results than if you break it in 2 points where the slope is.
Oh, I see.
So this is what I'm trying to say, that, you know, there might be some parts of the planet that it's easier. I mean, you're getting better results because, you know, you're the gradient between 2 nearby points, which happen to be at the end of your signal. It's small.
So there are two things we did for this data. So the first is we regraded data down to a very low, very coarse gradient. So theoretically, there's no very sharp gradient anymore. And then also, when we're doing spherical Fourier transformation, we truncate some portion of the frequency out.
Because, yeah.
To get rid of the sharp gradient.
Well, if you ever go to higher resolution, think about the, you know.
Sure.
That's it.
Other questions? Yes. So that was a standard transformer, vision transformer architecture. So there was no Fourier stuff at all. And I think we've come to the gradual realization that those models end up giving us artifacts near the poles because, you know, the North Pole and the South Pole are a singularity, whereas they interpret this to be like a flat image. So the entire top of the image is actually 1 point, not several points. So they give us artifacts over there. So we are starting to move away towards the spherical representation.
I would request everybody for another round of applause for Romit.
Thank you.
Just to check, we don't have any more questions online.
Oh, yes. Let me. What's going on?